Thank you.
Great. Thank you very much for coming. Our background is mathematics and mathematics education, but we got involved with a large NSF math-science partnership where most of the work was done in middle school and high school science classrooms. So we wanted to offer a snapshot of some inquiry-based learning that is happening in that context. And the one in particular that we chose had a heavier mathematical piece so that we could still talk about that. So we wanted to give you a little bit of background of the project where the curricular units came from that we're going to talk about today. So this was one of the big 5-year MSP NSF grants, and it spanned across the nation. We had 4 sites: West Coast, Rocky Mountains, Great Lakes, and East Coast. We targeted middle school and high school science teachers, and our focus was on promoting the environmental science literacy, and we did that through learning progressions, development and research, offering professional development for the teachers, and then assisting when they did the actual implementation in the classrooms as well. The 3 curricular units that were chosen were biodiversity, the water cycle, and the carbon cycle. And then in each of those units, the strand that went through them were quantitative reasoning, culture, and place. So there was a lot going on in a lot of different places. So learning progressions, that was the big piece that was on this grant. They are research-based. They have 4 levels. At the lower levels of the force dynamic accounts, it is a lot of actors and enablers. The tree needs sunlight to grow, to help it grow. Those kinds of descriptions. There may sometimes be hidden mechanisms. When they describe where water goes, they might say, well, the water goes down, but they don't talk about gravity or why that happens. And so those mechanisms become apparent at the 3rd level. They may talk about evaporation, that there is the mechanism of the heat from the sun. It isn't just because it's sunny out, that there's a piece behind it. So those are all research-based from student assessments and where the students are actually at. And then the 4th level is the model-based account, where we hope they are doing principle-based and evidence-based reasoning. And that is aligned with standards and the hope of where high school students are at by the time that they graduate. In this project, we did identify 8 teaching strategies that are certainly nothing new, but they lent themselves well to moving students along the learning progression. So we labeled them learning progression teaching strategies. So I just wanted to list them here, and the reason that we're here today to talk is about 4, 5, and 6 mainly, where the teachers really are attending to the student ideas that are coming forward. They're offering authentic inquiry for the students to do, and then prompting that reasoning to take place as well. So we'll talk about those in a little bit. The professional development that was offered to the teachers was certainly a large piece of this for them to be able to implement in their classrooms. I think of this a lot like the workshops that are offered for the new professors in IBL, that kind of a thing. That even in the science, a lot of the teachers weren't used to encouraging the students to be the scientists themselves, that they wanted to get in front of the classroom and do the demonstration. And so the piece that became the inquiry-based learning was for the students to get to be the scientists themselves. So they had normally these 2-week-long meetings in the summer. They got to be the students, so they got to do the experiments themselves. And so not only did they get to do the inquiry, but they got to see the PD leaders model how to be the instructors in an inquiry-based setting. Another big piece of it was learning about learning progressions. This was a new thing to a lot of the teachers. So the goal was that there were formative assessment pieces built in so that the teachers could know where their students were at, kind of identify them on the 4 levels of the learning progressions, and then have appropriate questions and activities for helping to move them along the learning progressions. It was a very large study, hundreds of teachers, thousands of students, so it was spread nationwide. This last year, we conducted a case study of 16 of those teachers, 4 in each of the sites. Bless you. And they were spread out by site, by strand, and by middle school and high school. So we recently reported at a national conference about the research aspect of that. And today, we wanted to get even more specific, and the 3rd teacher here, Mr. J, taught at a middle school in the mountain region, and he taught the water cycle. Previous to teaching, he'd been an environmental engineer for 20 years, so he was very comfortable with the mathematical side of what was happening. So we found that most interesting for today. When we did this case study, we observed 5 classroom lessons. We interviewed the teacher multiple times. We interviewed the students in a focus group. We interviewed an administrator. And then we also had the teachers fill out some surveys and teacher and student assessment data. So there were multiple places that this data was coming from. So here's where you guys get to use your sheet of paper. There were many process tools throughout these, and this was the goal of getting the students to reason and to think. And so the first one that they did was about the pathways of water. So in the middle of your paper, if you would just draw a puddle of water, just something that simple. So we tell the students that we walked outside the schoolyard that day and we saw a puddle of water sitting on the softball field. And then we asked them, where could that water go? So what happened to it? Where does it go after the puddle? And where was it before it was a puddle? Where could this water have come from? So if you guys would take a minute and kind of think about that, and you can write down some ideas or sketch some pictures, and I'll give you just a minute to think about that. Okay, thank you very much for taking the time to do that. I'm going to share a little bit about what the students had, and then if you guys have other ideas, I'd love to hear them. In the interest of time, I'll share with you what we heard from the 7th grade students. They were in the Rocky Mountain region, so 14 of the 16 students said that that puddle came from snow, that was where it must have come from. One did say rain and one did say precipitation, but snow was certainly the predominant answer. And then where it went was that it gets dried up or it evaporated. Those were the two most common things that we heard. What other kinds of things did you guys talk about? Other ideas? So one said it soaked into the ground, or animals drank it. That's another answer, right? It's certainly a possibility. She's got the microphone for you.
It's humid enough that the puddle... Okay. It's humid enough that part of the puddle stayed there, the rest of it, due to gravity, went down into a drainage ditch.
Okay, so some of it may have stayed there, right? Maybe it didn't go anywhere right away. Drainage ditch, so runoff. Runoff was an idea that none of the students mentioned, and only one of the 16 mentioned that it could go into the ground. Everybody else was talking about the sun and that was what happened to it. And there were some students that were a little more technical with their scientific language, or talked about multiple cycles of the water cycle, that first it had to evaporate and accumulate in the clouds, and then it precipitated, and that's how the puddle existed. So they went through that cycle multiple times. But again, the runoff being the big thing, that it didn't talk about it coming from somewhere else, that it was, on a field higher above, and that it ran down into the softball field, those kinds of ideas. So one of the big questions that the water teaching experiment is trying to get at is this idea of multiple pathways that water could go. That we have the traditional water cycle that we think of with the circle, but does it really always just go in those one places? What else could happen to the water? So the teaching experiment itself is what I want to share with you now. This was the unit that was implemented. It was a week long. It was meant to be week long. We found that most teachers took actually 7 or 8 class periods to implement it. And it was developed using the 5 E's. So the big thing was that they wanted to engage the students by asking them how much water falls on your schoolyard and where does it go. So that was what made it the local context, that they could do an authentic inquiry with it. And they did it through multiple explorations, asking the students to provide the explanations and the elaborations. And then the evaluation at the end was a very wide open final evaluation of what did you learn in this unit. The teacher had the ability to do this because this was an elective course. So that was a nice piece of it. So they started out by drawing what they understood the water cycle to be, and then at the end we'll see some examples of the more sophisticated understandings that they had. So the explorations. The students, this is that when I talked about that they get to go out and be the scientists. So they had the simple inclinometers with just the piece of paper and the little washer hanging from it, where they could go out in their schoolyard and measure the angles, and that was when they learned things like the parking lot wasn't completely flat, that it was graded so that water was going in a certain direction. They went out with jugs of water and poured it, and it often took a whole jug of water to pour to see which way it was going. They also got to go out and do experiments with the evaporation, transpiration, and infiltration. So they measured an amount of water that they put into a baking pan, and they took it outside Friday, and then came back and measured it on Monday. Well, there are about 3 different groups that did this that had very different answers. So they got to talk about the kinds of things that might have happened. That maybe it did rain or snow over the weekend, and so that was why there was more when we were expecting less. Maybe an animal drank out of it. Maybe it got knocked over. So they got to have all those conversations about what happens with real data when you're doing those inquiries and how do you deal with those situations. The other thing that the students really enjoyed was that they got to be the experts. It was kind of set up as that jigsaw where you are the infiltration group. So you're going to go do this experiment and then come back and talk to the class about the rest of it. So I'll let you read this quote from the student about when they got to come back together as a class. So even though in science, I think one of the big pushes is that the student should be the scientist and do the experiments themselves, they can also learn from their peer doing the experiment. And so that was a big piece of it, that they needed hands-on inquiry, but they didn't need to do the whole piece, that they were willing to, that they had observed their peers do these things and that they had those conversations together. The big exploration that I wanted to talk about that they do is they get a Google Earth snapshot of their schoolyard, and then they lay a grid over it, and the grid had, I think, 220 squares on it, and they decide all the different types of surfaces that they're gonna mark on this grid. And this particular class came up with 7 different surface types. So then they went back in their groups and had to start coloring those in to see how much was grass, how much was asphalt, the trees, the school, those kinds of things. So even in their groups, they had to make decisions about what do we do if it looks like it's a half a square or a quarter of a square, or if we can't even estimate how much of a square it is. You know, what do we end up doing? Then they came back together as a class and all reported the percentages that they had, and they came up with this table. So on the side here, we have the different types of surfaces, and then the groups. And so we came up with what were your totals and what was the average. So these are all percentages. So almost every group had over 100%. And that was in those decision makings that they did, right? They decided, oh, well, this square is 2/3 grass, but I think it might also be 2/3 asphalt. Like in all those kinds of decision makings, that's where they came up with those numbers. So as a class, it wasn't horrible. The average was 110%, but immediately the teacher wanted to look at the data and see what they found. So he asked the students to look at that first row and what they observed. And immediately for the sand and the gravel, the students identified that number 29 from group B as being different than the other numbers. So for me, this was an example in a science classroom of a mathematically rich conversation that could happen. And they did talk about that it was different, but they didn't get into any deeper of the statistics or use the word outliers. And so it was certainly that opportunity. Yeah, I can see you over there just jumping at it. It was certainly that opportunity for, you know, the integrated STEM experience. And this classroom had more of it than a lot of others, but there were pieces that could have been added. So they got to see, because the spreadsheet was on the board, when they took out 29, they watched that average drop from 10.7 to 6. So immediately they knew that their overall was getting closer to 100. So they went through each line and talked about it. And sometimes it was purely a mathematical, you know, one of these things is not like the other with the 29, but they got down to synthetic turf and said, man, those are all pretty close. Like, I don't really think there's one we should get rid of. They kind of make sense. Well, that was the football field that was on the campus, and so that was rectangular, and so hopefully those numbers are pretty close. But they made those connections. They were the ones that offered those solutions. And then when they got to the bottom, at mulch and rocks, that caused quite a conversation, because you have kind of the bimodal thing going on here, right? 1, 2, and 5, and 9, and 12. So the teacher brought it back to the local context of their schoolyard. Said, well, what does that mean for this number 1 to be here? And so one student says, well, that means 1% of our schoolyard has rocks on it. And the teacher says, okay, so is that about right? You're the ones that are here every day. You're walking from, you know, the bus stops to the school. You're out playing in the fields. Do you think that it's closer to that 1 to 5% range? Or do you think it's closer to this 9 and 12? So they started talking about all these other surfaces again and said, yeah, you're right. I don't think there are very many rocks. Most of it's either grass or sidewalk. There's not a lot of that. So they chose to omit both the 9 and 12. So when they were all done, they got down to 100.7. So they did a lot of nice reasoning that was both mathematical and kind of the local context type of reasoning to get down to that percentage. And so the reason that they did all this is that they wanted to know, if we have all these different surfaces, Some of them are going to evaporate at a faster rate, some of them are going to have more runoff, some are going to have more infiltration. So once they did all their explorations, and then here's a student that was really excited about the numbers that were on the board. So this was the student that while they were sitting there drawing and filling in their squares, he wasn't really sure what the point was, right? Sometimes you get so involved in the middle of an activity, you're like, I don't know, my teacher told me to color in these squares. I'm really not sure what we're doing here. But for him, when it all came together and when they had that quantitative reasoning conversation, he understood what they were doing. So that was a very important piece for this particular student. So now that they had percentages, they had to figure out what to do with them. So they also looked up local data to see how much rainfall happened in their city in a year, and they looked at the square footage of their campus, so how many actual gallons are falling on our campus, and then out of those gallons, what percent do we think is infiltrating versus running off and doing these things. So there was a logic model that we offered them, and this student really enjoyed that he had to explain something. It wasn't just the teacher that was explaining, but when he was working through it, that it meant more to him. So I know this is crazy looking, and it looks just as crazy, of course, to these middle school kids when they see this. But this was the logic model that they were going to do with all of their experiments that they had. So I'll take just a minute. I want to zoom in on the top half of it, so it's a little bit easier to see. So they had to take their 7 surfaces that they had and decide how they fit into these 4 surfaces that are listed here, and then decide, well, what percentage of it that was on the roof, on the asphalt, on the grass. And once they did that, they could then start doing these calculations to figure out how much actually evaporates and returns to the sky, because these different surfaces are going to have different evaporation rates. So then when they get all the percentages, they can have their total. And so remember, the big question they were asking is how much water lands on your campus, and how much of it can you use? Where does it go? What happens to it? So now they know how much has evaporated. There's also a little piece about transpiration. And then on the bottom half, they'll also talk about infiltration and runoff. So that's the bottom half here. So they can see what actually makes it to the groundwater supply. Like that's kind of the final. And so we didn't get to observe the last 2 days of the classroom, but there was when the teacher brought everything back together. And so they could get data from their school about how many gallons of water their school uses versus how much is actually falling and going into the groundwater supply. So they could begin to have some of those citizenship conversations. Another thing they could do with this logic model is that they could change the numbers, right? They say, well, we found that 20% landed on the roof, but what if there were more buildings on campus, because they're talking about building a new gym, and now it's going to be 40%, how is that going to impact these final numbers? So that was the elaborate part. And then the evaluate part, here's a final project from one of our students. The circle of life, the water cycle, this was what was important to this gal. And so it still has a fairly typical water cycle feel to it, but instead of just buzzwords like evaporation or precipitation, she explained a little bit more about what was going on, and that in the water cycle is now her school, that's now a piece of it. It's not just that it lands on a field or it lands somewhere, but it's actually her school is where some of the water is falling, and then here were those different pathways that we talked about. And at the beginning, she was one of the students that said it all just evaporates. And so now she's seeing that it's going multiple ways. That's her post-assessment again, and this is her pre-assessment. So this was her understanding of the water cycle beforehand. So an example of that more sophisticated understanding moving along those learning progressions. So students learning, teachers teaching, all the combinations of the above. These teaching strategies that we identified became a big part of the professional development and the conversations that happened when we interviewed the teachers. And so here's the 8 that are here again. Again, the ones that we focused on for this presentation were 4, 5, and 6, that we really want to attend to where students are at with their ideas so that we can help them build and move along the learning progressions. And that in science, a frequent way to do that is through this authentic inquiry and asking them to do the principle-based and the evidence-based reasoning. So what I wanted to show you here was that in one of the interviews with the teacher, Mr. J, we asked him which of these 8 teaching strategies he used. And he said that he used all 8. And the 5 days that we were there, we observed all of them except number 2 and number 8. And number 2 was the planning portion based on where students are at from the pre-assessments. So that's really hard to see when you're in the classroom, right? So that's why that wasn't there. But the last piece about citizenship practices we didn't see in the first 5 days we were there, but then when we interviewed the students in the focus group, they talked a lot about water runoff. That was kind of the new big thing that they were picking up from this grant or from this project. And next door to this particular school was a farm. So they talked about how it does matter what happens to the water on their schoolyard because it runs off to the farm next door. And that matters because a lot of people in the community eat the food that farmer's growing. So even though we didn't observe the teacher doing it, I think it just happened at the end after we left, and the students certainly talked about the fact that it happened. So then we asked this teacher, well, if your goal is really to help students have a more sophisticated scientific understanding of the water cycle, which of these teaching strategies do you think are the most important? So these were the ones that we've been talking about a lot today, the 4, 5, and 6 that he really emphasized. But he also talked a lot about number 1, about big ideas, that it was really important to bring students back when you have this big, long, elaborate project to what the point of it is. That we were engaging you by asking how much water fell on our campus and where it went and what kinds of things happened to it. So that was a piece that he certainly felt was important. Now, when you asked him about other priorities, he would talk about other teaching strategies. So to him, one of the other important things was having all of them available, and then depending on what your focus was, you could use the appropriate ones. So here is his quote about moving students along the learning progression. So in this one, the teacher begins to really address the difference between the students at the different levels, right? That at the lower levels, he feels like the getting your hands dirty inquiry part is very important, and at the higher levels, really the reasoning and asking the why and the how questions. An emphasis that this teacher really placed on learning was the students' ownership of the learning, which is why they did things like the jigsaws and they become the experts. So the last thing that I wanted to share with you was a quote from a student about authority in the classroom. So for me, reading this was definitely the preaching to the choir, right? That's what we're trying to do. But to get that out of a 7th grader in a focus group of 8 other 7th graders, and to try and get that detailed of a piece of quote from them. So this work was generously funded by the NSF, and we do have a webpage that does share all of the materials. I know you mentioned that in your talk about you don't always see what it was that they implemented, so we wanted to let you know that all of the research is published there, as well as all of the modules that the teachers did as well. Thank you guys for coming.
Bill McKenna with EAF. That was really cool.
Thank you.
That was really great. It brought a whole bunch of stuff to mind.
Good.
And one was, just a quick comment, a friend of mine made these bins, took plastic bins and made runoff displays.
Yes.
And you can do asphalt, concrete, grass, dirt, and you can actually see it happening. My question, though, is you were using the 5Es. I know that UTeach uses that. How did you guys decide to use that model for lessons?
So this was developed by professors at Montana State and the University of Arizona. And so that was just their preference of their, each one that was developed by a different group of people, so it was however they wanted to go about it. And so they are certainly more inquiry-based inclined professors, so that was just their choice. And they do actually have some pretty neat, they call them watershed tables, and that was one of the ways that we were able to support teachers, was that those existed on the project, and so we could go into the classrooms and help the teachers demonstrate those projects. And so it was a whole watershed, and then you could demonstrate what would happen if there was a landslide here, oil spill here, and especially in the Rocky Mountain region with things that happened in the last couple of years, fires and floods and those kinds of things. So these were very elaborate, large things where they even had little plastic cows and all kinds of things. But what's neat about it is that you can certainly do it with pretty much just a plastic tub, right?
Yep,
So it's very accessible.
You can make them on the cheap. Yeah.